everyone, my name is Ayush Kumar. Welcome back to my channel. So today we are going to talk about data structures and application, in which we have taken a research paper, uh, which goes by the name Algorithm and Data Structures for New Models of Computation. So basically, this presentation explores the design of algorithm and data structures for the new computational models that have emerged with the advent of new technologies such as flash memory and heterogeneous multiprocessors. Let's get started. So this is the abstract in which basically in the early days of computer science, the community settled on a simple standard model of computing and basic canon of general purpose algorithm and data structures suited to that time and to that particular model. But with isochronous computing, heterogeneous multiprocessors, flash memories, and cache and other anisotropic memory, these were distributed among different languages, graphical coprocessors, and so forth. The basic canon of algorithm and data structures is not enough for that time. And as the hardware getting better, the algorithm and data structures also should be efficient and faster. So these constraints motivated the development of elegant algorithms with broad utility, such as example we present four algorithms that were motivated by specific hardware requirements but are generally useful, which are reservoir sampling, majority of a stream, B heap, and compacting of an array in log n times. Let's get to the next part. So basically, in this whole video, we are going to talk about the new algorithms. So let's get started. Algorithm and data structures are foundational elements of computer science, serving as a building block for efficient problem solving and resource management and software development. As computing models have evolved from early single processor system to today's complex architectures involving heterogeneous hardware and distributed environments. So there are many such energies which are efficient and optimal, uh, which can be used for optimal memory usage, which also requires innovative solutions that to enhance the functionalities of a hardware. In this context, the paper presents four innovative algorithms, which I said earlier, which are same the reservoir sampling, virtual memory aware heap, and majority in a stream. And there are specific designed to tackle these real world constraints. Each algorithm exemplifies a balance of elegance and utility in each part of the respective task, showcasing how an understanding of an hardware requirements can lead to effective and broadly applicable computational solution. We have a literature survey in which there are like similar research papers which are found, which are research articles focusing on specific areas like streaming algorithm, energy efficient algorithm, and algorithm for parallel processing. And there is also publications around that, which includes ACM transaction on algorithm or IEEE transaction on parallel and distributed systems. So we have another research paper which was Introduction to Algorithms by Thomas H. Corman, Charles E. Uh, Laserson, uh, Ronald L. Rivest, and Clifford Stein. This book covers fundamental algorithm and data structures, providing a strong foundation for understanding their evolution and application. So we have this three research areas, and we have some certain key findings. So at first we have flash memory algorithms. These techniques are usually used for optimizing data storage and retrieval in flash memory, including where levering and garbage collection. So flash memory uh, loss of flash memory would be a huge burden. So this technique is basically used to recover the data and the contents through the flash memory. And next we have heterogeneous multiprocessor algorithm, which approaches to efficiently utilize the strength of different processing unit and manage data flow in heterogeneous multiprocessor system. Next we have new data structures, which are the new inventions, exploring of novel data structures designed to leverage the unique characteristics of new computational models. We have a few emerging trends following this thing. We have a cache aware algorithms like the B heap reduce cache misses, enhancing performance in memory intensive application. Streaming algorithm, efficient algorithms such as reservoir sampling and majority in a stream cater to real time data needs in IoT and online services. Next, we have parallel and distributed processing. So, parallel algorithms such as parallel array compaction, leverage multi-core, and distributed system for improved scalability. Next, we have improvement highlights by the research paper. So, um, improved memory management. The B heap reduces page faults by optimizing memory use, outperforming traditional heaps in modern memory hierarchies, which is again a good thing. And next, we have efficient stream processing. Algorithms like reservoir sampling and majority in a stream efficiently handle real-time data using limited memory. Next, we have parallelism and scalability. The parallel array compaction algorithm optimizes performance for multi-core system, making log and time feasible with just n hardware. Next, we have the architectural model for the whole research paper. So the architecture model in this paper is it is very different from the traditional and single core processor and uniform memory model. So the new architecture must have like isochronous system, heterogeneous processors, distributed system, energy constraints, and real-time streaming data. So isochronous again, which handles the tasks which are being executed at intervals and with precise timing, and heterogeneous process again, it basically does is manage the general purpose CPU and specialized GPU or co-processors algorithm. Must have these diverse resource effectively. Next, we have distributed systems, which again incorporates into distributing computing where multiprocessors or machine work could be done over a network, each with its memory and processing power, for example, like cloud and other things. Next, we have energy constraints, particularly in mobile devices and large scale cloud systems. Energy efficiency must be a primary design considerations. If you are building something, then it should be very much energy efficient, or else there'll be many problems to it, and also it's not good for the nature. Next, we have real-time streaming data. Algorithm must process continuous data stream efficiently without knowing the size of the incoming data in advance. So that basically means like it should continuously process the whole data efficiently, and it can handle like larger size, larger size of data efficiently, such as sensor network or online services, like servers. Next, we have the methodology sorry methodology, uh, which you have two main things which you are going to cover, which are reservoir sampling and virtual memory aware heap. So for the basic understanding, the algorithm in reservoir sampling is designed for stream processing environments where the total number of items is unknown. It is crucial in scenarios where only limited memory is available. Operations. So the operations which are performed in this is like if you take a random item from a stream of unknown size using constant memory and a simple counter. Next, we have real world application for it, which can be used in again, which I have said earlier, which are sensor networks where sensors continuously stream data, but storage is constrained. Next, we have virtual memory aware heap, which is also called as like B heap in short form. Next, we have the context for it, which basically means like the heaps which perform poorly in modern memory hierarchies because of frequent page faults. So this is where the use of B heaps comes in, which is more efficient and it can handle the page faults very easily. So the B heap operation improves on this by keeping significant portion of the heap within the same memory, unlike the other heap, reducing cache misses and page faults. We also have a few real world applications such as it can efficiently prioritize the queues and heap sort algorithms in sort with large data sets. Next, we have the results for the overall thing, which again, but it significantly improves with the performance over traditional approaches, which is again a good thing. Anything which is efficient is totally a good thing. So that's what this research paper actually highlights. We have the reservoir sampling, which again demonstrate the efficiency in selecting random items from large stream using minimal memory. Next, we have majority in a stream, which successfully identifies majority items in streaming environments using constant memory. Behip, which should reduce page faults and improves the performance in priority queues implementing when working with large data sets. Compacting an array achieved efficient array compaction in log n time using parallel processing, making it highly suitable for systems with multiple processors or distributed setups. Next, we have come to the conclusion part. So basically, all these algorithms include energy efficiency, multi-core processing, complex memory hierarchies require new algorithm data structures that basically addresses these challenges. We have also the four algorithms, which is again the reservoir sampling, behaves, and others, which basically helps us to develop to more, uh, move to a more beyond traditional methods and adopt new hardware-specific techniques. There is a clear need for renewed research and development in this area, with a focus on integrating these new algorithms into standard libraries for broad adoption. The ultimate goal is to ensure that developers have access to efficient hardware aware tools that can optimize performance in real world applications. Um, but there are also a few downsides of the whole thing, is to like not every device has the multiprocessor things. So there is that one downside of the of this research papers, because like most of the things can easily run on the, like, they're more good to work with the multiprocessors than the single core, and like most people can't afford the multi-core processors. So that's a downside. So that's it for the video. I hope you like the video. uh, Thank you.